Okay, welcome back to the third session of the day. I hope all of you had a great lunch, and you have to wait for 1 hour for your tea or coffee, and in between we have two very exciting talks. First speaker of this session is Preeti Kharb from NCRA, who will be talking about the radio emission in low luminosity AGN.
Okay, thank you. Okay, first of all, I want to say I'm so excited to be here. I don't know, for people who don't know, we had organized the first conference at ICTS 10 years ago. And so this is very, bringing back nostalgia. So I want to talk about radio emission in low luminosity AGN and basically some of the work that our research group has been carrying on. What I want to stress is that improvement in sensitivity has been a very important factor in getting some of these results. Therefore, the SKA is definitely going to, with its improved sensitivity, is going to really revolutionize the study of low luminosity AGN. By low luminosity AGN, I include Seyfert galaxies and liners. Seyfert galaxies, as you know, were the ones which were first discovered by Carl Seyfert in 1943, and they were identified because of their star-like nuclei and very prominent emission lines in their optical spectra. And liners were discovered much later. They stand for low ionization nuclear emission line regions by Tim Heckman and others. And the difference between Seyferts and liners was that the low ionization lines were much more prominent in liners compared to Seyfert galaxies. And both these class of AGN belong to the radio quiet AGN category. And by radio quiet, I mean that they have these ratios of radio flux density at 5 gigahertz to the optical flux density in the B band. That ratio is typically less than 10. So this 10 came about because of this work which Ken Kellerman and others had done, where they found that when they took this ratio, their sources from the Palomar Bright Quasar survey fell into these two categories very clearly, and the division was around R equal to 10. So this definition has stuck, but I do want to stress that there is nothing very sacrosanct about 10, and a lot of other samples don't really see a very clear divide. So we can keep that in mind. And Kellerman already found that radio quiet AGN probably make more than 80% of all AGN. So this is the vast majority of AGN. They're going to be very, very important when SCA comes around. So for a working definition, we can use this picture. So on the left panel, you have a typical radio quiet AGN, and it's a very famous one, NGC 1068. So here, the green that you see is starlight. In spiral arms, there's a spiral galaxy, and the pink-blue emission that you see are radio outflows. And the first thing to notice is that the radio outflows are small, confined to the host galaxy itself. On the other hand, a small minority of AGN are these very impressive ones that we know of. So this is a very famous radio loud AGN called Hercules A. The optical elliptical galaxy is only of that much size, and the sizes of the radio jets shown in blue are, of course, much larger and go on to hundreds of kiloparsecs. So for the purpose of the talk, we can just remember that radio quiet AGNs are the ones where the jets are small and they kind of are confined to the host galaxies. So the results I'm going to now share with you have definitely come about because of improvements in sensitivity. And this has led us to kind of find out more about the magnetic field structures in these radio quiet AGN, and also the discovery of multiple episodes in AGN activity. So let's start. How it started was in the 1990s when radio surveys of radio quiet AGN and Seyfert galaxies were carried out. So these are, for example, two images from one of these earlier works, which was carried out by Steffi Baum and collaborators. And so these are radio contours of these galaxies, Mercurian 231, NGC 3516. And this was a study carried out with using the Westerbork synthesis radio telescope in the Netherlands. Had some arcsecond resolution Of course, you can immediately see that, comparing it to, for example, Hercules A, the radio structures are more complex. It's not very clear if there is any kind of directional outflow. I mean, maybe here in this it's a little bit better, but you don't see much on the other side as well. So this is because of the lack of sensitivity in those earlier observations. And because of this, there was a lot of debate on the true origin of the radio emission from these radioquiet AGN. It was also suggested that perhaps stellar-related processes were contributing to the radio emission in these AGN. And there is some truth in that as well. But as observations have become more sensitive, so this is a very large array image of 1068, NDC 1068, which I also showed in the previous slide. Now you see a contour image, and you see that there is a directional source. What may look like a jet, but it's still not a simple source. You can see that, for example, this bright knot here is actually not the core. It's not the origin. This is not where the host galaxy nucleus is. The nucleus is actually somewhere here. It's not very pronounced in the radio. This is just a little portion of the jet. So it is complex, but when you start looking at high resolution radio images of radioquiet agent, you start seeing jet-like structures. And because of these improvements in sensitivity, resolution, etc., there is some support to the idea that these probably are agent-driven radio outflows. So let me now come immediately to one of the Seyfert galaxy, which my student Sharmoli Ghosh is studying, and Sharmoli is here in this conference, and she actually has a poster on a very colorful poster on this object. So I would encourage you to take a look at that. So this is radio. So these are very recent observations with the VLA, and now because of sensitivity, we are able to pick up much more weaker polarized emission from these galaxies. So now here is a radio optical overlay. The blue-red emission that you see is the host galaxy. It is a lenticular galaxy, and the green contours are from the radio, the VLA. Here, this image shows the red ticks that you see are polarization vectors with lengths which are proportional to the degrees of polarization. So you can see there is a lot of polarization. This goes almost as high as close to 20%. And then you can see that the inferred magnetic fields for optically thin emission is perpendicular to these vectors. So the B fields may be aligned with the outflows in this case. They seem to be aligned here, but then they kind of flip here. And there are interesting things going on in this particular source also in terms of spectral index. So we think there is a hotspot here and B field compression. Now, this kind of work was not actually possible, several years ago because polarization was hardly detected in most of these Seyfert galaxies. But I think with the improvements in sensitivity, you can now see this. This is an image of the same with GMRT. And again, the ticks are actually polarization vectors. But here I want to stress another point that GMRT not only picks, of course, this primary lobe, but starts picking up even diffuse emission beyond the primary lobe. And I think this is going to be also the focus of our talk today, that as you go to more sensitive arrays, and especially at low radio frequencies, you start getting a much more complex picture of these AGN. What is very exciting is this result that Sharmoli has got on this particular galaxy. So because we had polarization data at one frequency, she eventually got a polarization data with the VLA and also GMRT at multiple frequencies and was able to create a rotation measure image. So this is just the contours are presented here, and the color that you see is rotation measure. So rotation measure is basically is proportional to the electron densities and the magnetic field along the line of sight, magnetic field strength along the line of sight, and then the path length through which the polarized emission traverses. And so you can see here that some kind of gradients are observed in the rotation measure. So the bottom panel actually shows these gradients better. So this slice here across the lobe, and then there's another slice here, are shown in this blue and the red. So what was very exciting was that there is a rotation measure gradient which seems to be reversed in the two lobes of this galaxy. There is also a rotation measure gradient along the jet, which is we believe due to something else, which we can discuss later if anybody is interested. These RM gradients actually have been observed in radio loud AGN, and they have been suggested to be signatures of helical magnetic fields. because it is, I mean, the way you would get a gradient is either a gradient in the electron densities or the B field, the line of sight B field. And there is no reason to believe that you would have this NE gradient in a certain way to kind of produce this RM structure. So one way to interpret this is that the B fields are actually kind of either coming towards you or going away from you in a helical magnetic field structure. So this is a cartoon to show what could be happening. So you have magnetic fields anchored on the accretion disk black hole system, and as it rotates, you have these wound up magnetic fields, which may give rise to these kind of rotation measure gradients. This is very exciting for us, because if this is confirmed also maybe by even more data and more sources, this could suggest that the jets even in radio quiet AGN could be magnetically launched. Okay, so this immediately kind of bridges the gap between radio loud, radio quiet AGN. So it was believed that the radio loud AGN jets, which are very, very large, are probably being driven by the Blandford-Snayak or Blandford-Payne mechanisms, which require this either from the accretion disk or the black hole spinning, that you would extract energy into the jets, which are very powerful. If that is also true for radio quiet AGN, then the difference between radio loud and radio quiet AGN is not going to be an intrinsic qualitative difference, but rather a difference in quantities. Maybe it's more quantitative. Maybe there is one factor which has to be changed, which could kind of then produce these different AGN subclasses. So that is very exciting for us. Now, let me show you another Seyfert galaxy. This is NGC 2639. So here is the spiral, rather S0 type of galaxy in the green. And this white contours that you see are actually lobes that are observed with the GMRT. And in fact, so this is at 700 megahertz, and the dotted line is showing emission at 300 or something, 325 megahertz. Previously, there was a radio lobe known in this galaxy, which is shown here in red and actually zoomed out here. That is from the VLA. So the VLA had already identified a north-south bipolar structure of extent 1.5 kiloparsec. But GMRT at 735 megahertz picked up a much larger bipolar structure. And all the VLA emission is actually confined to the core of the GMRT image. And this galaxy, at the core of this, when was looked at even higher resolution VLA data at using the VLA-A array, there's another bipolar structure in a completely different direction. And similarly, the core of that with VLBI or VLBA, a very long baseline array, finds that there is a core structure in a slightly different direction as well. So there are all these nested structures which are present in this Seyfert galaxy, which suggests that, and of course, this is not the only example. There are several other examples, still a handful, but there are examples where nested magnetic field, nested radio outflows are seen in these Seyfert galaxies. So, so this was actually work that one of our visiting students carried out, Vaishnav Rao. And so what he did finally was to use these tools to do some kind of spectral aging analysis of these different lobes. And he found that the spectral ages of these three different lobes were 34, 12, and 3 million years. And for using this, we could derive an AGN duty cycle, which is defined like this. The time the AGN is on divided by the time on plus off. And for 2639, we could actually derive a duty cycle of 60%. So this was also very exciting. So 60% of the time the AGN is on during its lifetime. Now, the next thing was when we looked at the gas, molecular gas in this source. Now, this is an image of the molecular gas, CO gas, from the Karma Edge survey. And there was a kind of a hole that was seen in the CO gas emission of extent 6 kiloparsecs, which is kind of very coinciding very nicely with the GMRT lobes. And this is a moment 2 image of the CO map. And you see, you may not see it very clearly, but basically there is increased dispersion at the edges of this radio structure, which is seen. The bottom 2 panels are the Galax images. So this is far UV emission, and this is near UV emission. And in both the cases, we also find some kind of deficiency in the UV emission, which we suggest to be star formation quenching. And so what you're seeing is gas evacuation and also star formation quenching. But the fact that you may have increased dispersion at the edges of the radial lobes is suggesting that there is possibly both negative and positive AGN feedback, which is going on in this galaxy. And what is interesting is that perhaps the fact that it has so many different AGN activity episodes is also responsible for the fact for the reason that we see this hole in the CO gas and the star formation. So it's likely one very easy way to connect all this is that possibly this AGN feedback drives gas away, and then after some time when the AGN is off, the gas comes back and the AGN is like reignited. So you kind of are able to explain both the episodic activity and the feedback in this way. So that is it's a very nice picture that emerges. So now let me talk about how improvements in sensitivity can tell you more about these low luminosity AGN. So here are a couple of images of radio optical overlays of galaxies from another sample called the KISS-R. And the blue-red, again, this is optical light from the host galaxies. You can see them. Some of them are interacting galaxies. Some of them are normal spiral galaxies, S0s, etc. And the green contours are the VLA first, from the VLA first survey. These are radio emission from these galaxies. And basically what is detected is just radio cores. And these are extremely radio faint. So they're just a few millijanskis in flux density. So very faint radio cores are observed in the centers of these galaxies. So not very impressive. But when you look at them with VLBI, very long baser interferometry, so this is just the acronym KISS-R expanded here. And so let me just go through these images. So the first image is a galaxy called KISS-R 434. And what is seen is what looks like a core jet structure. There is probably a curvature as well, which is observed. The color is actually spectral index because we were able to detect this at 2 frequencies. So the spectrum is actually steep here. But what is interesting to note is that this curvature, when we observe this galaxy 4 years later, this curvature persists. So we still see the same structure in the second epoch of observations, which again tells you that this is all these features, even though they look very, they are very faint and they almost look like noise peaks, etc. I think they're actual real jets, but just weaker, much weaker. The extent of this is quite large. It's almost 150 parsec. So 150 parsec long jets are observed when you look at them with VLBI, even though the core, when you look at the VLA first data, which is arcsecond or 5 arcsecond images, you just see a point source. On the other side, there is another galaxy called KISS-R 618. It seemed to show a core jet structure, but 4 years later, the core jet structure seems to be having a different position angle in the sky, even though there is some emission in the direction of the original episode. And so this kind of structure is also very commonly seen in VLBI studies of radio loud AGN, which is some kind of nozzle precession. That is how you explain the results for radio loud AGN, which seems to also happen here. So overall, all in all, we are finding that the radio jets, even though they are weak and very not continuous, blobby, etc., they seem to show behavior which is not very different from radio loud AGN. And so one more thing was that this sample itself was selected on the basis of either asymmetric emission lines in the SDSS or double peaks. So I will tell how that also kind of now explains our results much better. We found, because we had these 2 episodes, we actually found that some of these sources had jet components moving at superluminal jet speeds. So this was one case, KISS-R 872. So this is the core and this is the jet component J0. And between 31st December 2018 and 5th November 2022, the jet component seems to have moved at 1.65, of course, with a large error times C. And then this is not the only source. We found another source, KISS-R 102, which also had these 2 compact components, which were kind of close to each other, which also seems to be moving marginally superluminally. So there seems to be also the existence of fast jets in these radio quiet AGN. which is also a little bit unexpected. And again, I want to stress that usually, till very recently, you wouldn't have looked at these agents with VLBI and actually detected jets. So it's because of sensitivity improvements that you are able to do this kind of work. And usually, radioquiet agents are not even followed up with VLBI because they're so dim that they're not really followed up. Radio loud agents are typically followed up on a very regular basis. So this is making the case that we should be also monitoring the jets in radioquiet AGN. Now, because these sources were actually picked up on the basis of spectra, we were able to model the emission line data. And we use this plasma modeling code mappings, which is kind of shown here. For example, here, these are line ratios, O3 by H beta and S2 by H alpha. And similarly, you can have N2 by H alpha and O3 by H beta. Now, the color that you see, the color grid, is actually produced from different models. And the data itself is here. The line ratios are here. And different models are kind of compared with the data to see what fits. And what was interesting to find was that this model called shock plus precursor model actually seems to explain the emission line data for these sources, especially the sources which had VLBI jets reasonably well. Now, what this model is that it's saying that it's not the shock from the jet itself which is ionizing the emission line gas, but rather the post-shock gas, the gas which is kind of undergone a shock, which then emits UV and UV emission and soft X-rays, and then photoionizes the surrounding medium. So this is another way to say that even though these jets are weak, they are impacting the emission line gas clouds around them. So they do things, even though they're tiny, they're doing things around their neighborhood. Now, there are some other cases as well in the literature where this has been found, and so this is 25 now? 4 minutes, yeah. The other cases, this is one such case. So this is a radioquiet agent J1316. You see in contour here. The two panels here are, the color is actually showing you data from VLT Muse, and this is O3 emission. So here, this is just total intensity, and this here is the dispersion again. So what is seen in this case, this very small, it's just a kiloparsec long core jet structure. But you see how O3 is enhanced at the edges of this small jet. And also the dispersion is enhanced in this direction, perpendicular to the jet. Similarly, in the CO emission, this is from ALMA, there is an increased amount of CO, of course, but there is also increased dispersion in the direction perpendicular to the jet. So these small-scale jets seem to be impacting the gas around them, not just the ionized gas, but also cold gas, etc. And so they are, carrying out feedback. There is also the teacup quasar, which has been found to kind of follow this behavior as well. So this is also in keeping with these hydrodynamic simulations that have been carried out by several authors, including Dipanjan and group, where they find that in the radioquiet AGN, there is an existence of both positive and negative feedback happening on these very small scales as the jet kind of emerges from the black hole. Okay, so now let me just put everything together. So what I wanted to stress in this talk was that radioquiet AGN or low luminosity AGN, I'm using this term interchangeably, they make the vast majority of active galaxies and likely show episodic activity, which of course requires high sensitivity to detect these past episodes of activity from these sources. And that is where GMRT and in the future SK is going to play an important role in picking up all this from the past activity episodes. And it's also possible that maybe all galaxies go through this kind of active phase. And this is actually in keeping with the results that are coming out from the Event Horizon Telescope for the Milky Way galaxy and the presence of the Fermi bubbles in the Milky Way. That maybe the Milky Way was active also at some point. And it looks like from the work that we've done on polarization that magnetic fields could actually be important in the production or collimation of these radio outflows, even in the very weak jets of radioquiet AGN. And this has profound implications for the radio loud radioquiet AGN divide. And these outflows, even though they are weak, they seem to still influence their surroundings. So they are being agents of AGN feedback. And SCAR with high sensitivity at low radio frequencies especially is going to really improve our understanding of low luminosity AGN in general. Thank you.
Okay, we have time for a few questions. Okay, here.
Preeti, so the slide you had the rotation measured. So is it that looking at the winding of the magnetic field, you can figure out that how fast is the spin of the...
We haven't done that.
And then you can also look at the H1 spectra along absorption along that and cross-check if you get the similar velocity dispersion.
Sure, that's a nice idea. So H1 spectra, you would expect, you mean gas rotation or something? Yeah, thanks.
Hello. In your initial slide, you showed the result of KISAR 434, where you showed this bending Z.
Yes.
Can you go, please, that slide?
Yes. Sorry. Yeah.
Yeah. So, therefore, how do you know that it is associated with the AZ and is not the separate source?
Okay. So these are VLBI images. The field of view of the VLBI images is actually very, very tiny. So it's going to be all associated with this one single source.
Okay. So
you're looking at a very small piece of the sky. So this is all, whatever you see here is all associated. Is your question about binary?
It's very, it's just a milliarc second scale. Okay. Okay.
Yes.
Good.
Yes.
Do we expect time variability in this radio quiet AGMs?
Yes.
And if yes, what would be the time scale of?
So, yes. So time variability is actually observed already, and depending on what scales you are kind of looking at, on the arcsecond scales, it's kind of few months. On smaller scales, of course, it's slightly faster. But we haven't actually. We did look at. I have actually looked at the variability in these, and so in the few years, of course, there is variability. There is variability for sure, and it's like of the order of like maybe around 25% or so.
So what are the redshift of these sources that you are getting?
Okay, so they're very, very close by. I don't remember the individual ones, but maybe like 0.01.
So any of them has been observed with Fermi?
No. These galaxies, especially from this particular sample, are actually not very well studied at all. But no, yeah. But why do you want to know that?
Because like I wanted to see how the multi-wavelength like emission and the variability looks for these sources. Because they seem very faint and
yes.
And the statistic is very poor, so I don't know how conclusive this will be, only the radio emission.
I see. I did want to say, because you asked not about these sources, but for example, NGC 1068 is actually detected with Fermi. It's one of those sources which actually has, it's a small jet. It's also not very radio bright, but it has actually been detected with Fermi. So, yeah. So whatever you're suggesting probably could be done, looked at.
Narendra.
These as these galaxies are like nearby, so have anybody looked into their ISM in neutral gas, for example, if there are effect of feedback in them?
We haven't done that. I don't think there is much work done yet on these galaxies, but yeah, that should be looked at.
Preeti, I have a related question. This one case where you showed the dip in the molecular gas distribution.
Yes.
Is that 12 CO or 13 CO? Because
that's a good question. I don't remember that.
Because in the
NUV, CO10.
Because the NUV, the dip is probably not that significant. Looking at least this image.
So you see, there is a ring here in the UV, and this emission here we think is from the AGN itself. But there is a ring here, which is probably seen much better in a grayscale image than this. And here also, I think that the ring is not so pronounced, but here again, you expect dust to be present. So.
Okay, any other question? We still have time for one more question, maybe. Okay, you mentioned that the superluminal motion in
Yes.
this case are not expected. Is that
Yes.
what I?
Yes.
Why is that? Because if the mass of the black hole or the spin is sort of similar to the
Yes.
other
Yes.
cases,
Yeah.
then velocity will not. I mean, the mass loading or momentum may be different,
Yes.
but the velocity will be.
So that's a good question. So I think it is generally there is a consensus that radioactive AGN jets are very slow, weak and slow. Because it's normally, I think before this, there was only one, that is not even a proper Seaford galaxy, but 3's Wiki 2 was the one, there was a claim that there was something very fast jet-wise. The issue, I think, has only been that these sources have not been, VLBI at multiple epochs has actually not happened for these. So there are only a handful of sources where people have done it. They have found not very high speeds. But until you follow them, you won't see it. Because also the point is that it's not that the jet is constantly moving at that speed. It's just one jet component which is moving fast. So to pick up that, you will need monitoring. Yeah.
Okay, so if there is no other question, let's thank Preeti and we move to the next talk of the session. The next talk will be on and I hope you can hear us. Your slides are visible.
Okay, perfect. Can you also hear me?
Yes, we can hear you. Yeah, so you please start. Yeah.
All right, thank you. Thank you very much. Thank you very much for the opportunity to speak. My apologies that I can't be there in person. The more I appreciate that I can give this talk remotely. So what I want to talk today about is about how we can unravel reionization with 21 centimeter galaxy synergies. And the question I have been asking myself essentially is like, first of all, like how did reionization proceed? And what was it ionization morphology? So put this short, essentially, what was the ionization history of the intergalactic medium? And which sources drove reionization? So do we have a scenario where the few bright galaxies drive reionization, you have a few large ionized regions, or do you have a scenario where more the faint galaxies drive reionization and you have more smaller ionized regions that grow over time? And so in this aspect, I was wondering if you consider that the two observables that we will have or already have, the 21 centimeter signal and also high redshift galaxies, what can we learn from them? And specifically, I have been looking at like what happens if you cross-correlate these two data sets. And I believe Andre has already a bit talked about this, but I want to dive a little bit deeper. So the first question you can ask yourself is actually, how does the large-scale 21 centimeter galaxy cross-correlation power evolve across cosmic time? And so I'm pretty sure you have seen this before. So in the top panel, you have sort of an idea how the 21 centimeter signal special distribution evolves across time. And what you clearly can see, we have this characteristic shape that as the galaxies form, the 21 centimeter signal goes into absorption. When heating begins, it starts heating, and eventually it becomes into emission also during the epoch of reionization. And the key thing is, as you can see here, I'm showing you sort of the sign of the cross power spectrum. And theoretically, you would expect during cosmic dawn and reionization sort of to have 3 sign changes. And to walk just briefly through this, like when the first galaxies form, you have sort of in dense region, you have a stronger Lyman alpha coupling. So these regions will have a stronger absorption signal in 21 centimeters. So your cross power will be negative. Then as heating then continues, you start heating around the galaxies. So your 21 centimeter signal becomes weaker in absorption and stronger in emissions. So you see a positive cross power here. And there's actually also then the next sign change when you go from positive to negative cross power is essentially tracing the end of heating. And for anyone who is interested, I think there was a really nice paper by Morivaki et al. 2024, and she really looked at this in detail. What I want to focus now is essentially on the signal during the epoch of reionization and after heating. So essentially when the ionized regions start wiping out the 21 centimeter signal and we see a negative cross correlation. All right, so what can we learn from these 21 centimeter galaxy cross correlation and cross power spectrum during reionization? So I think the first thing we need to think about, which galaxy probes do we want to tackle here? And I think here it's important to keep in mind that not only you want to have sufficient spatial resolution, so you know you can resolve the galaxy spatially, but also in redshift space. And for this reason, because you want to also resolve them in redshift space, so along the spatial scale, along the line of sight, what we often go to are essentially line emitters, because for those you can determine the redshifts rather well. All right, so cross correlations, what would we expect? So what I'm focusing on now is a lot of 21 centimeter Lyman alpha emitter cross correlation functions. And here I show you sort of a slice of a simulation where in blue, you see the 21 centimeter signal. So the darker the blue, the stronger is your 21 centimeter signal in emission. And in the red stars are essentially Lyman alpha emitters, where larger stars essentially indicate a larger or higher Lyman alpha luminosity. What you expect now if you cross-correlate these two fields is that on small scales, so just around the Lyman alpha emitters, you don't expect any 21 centimeter signal. So on these scales, you expect it to be anti-correlated. However, now you can imagine if you go from a galaxies like further out at a larger radii, it becomes sort of random in the end, like whether you hit an ionized or a neutral region. And so that is the reason why at larger scales, the cross correlation essentially becomes zero. It's not correlated anymore. Okay, so if you look at this shape, and you look at different reionization simulations, you will find a lot of simulations have predicted very similar shapes. So if you look here at the results from Kubota 2017, Henniger 2020, Weinberger 2020, Ranbeck, they all use kind of different simulations and reionization schemes or radiative transfer, but they all roughly find a similar shape. So you have the anti-correlation on small scales and the non-correlation on larger scales. But if you look now in detail, then you will start finding differences. And particularly if you focus, for instance, like on the small scale power, we can see that there are different amplitudes, although they have like a similar neutral fraction. So here we have minus 0.4, versus here we have minus 0.3 at a similar neutral IgM fraction. And so the question I was asking myself, why is that the case? What drives exactly the shape of the 21 centimeter Lyman alpha emitter cross correlation? And to do this, I decided I want to do two different reionization scenarios. So going back to my original question, like, did more the bright or the faint galaxies drive reionization? And to do this, I used the Astreos framework. And for those who are not familiar with this, essentially what the Astreos framework is, it couples a dark matter only n-body simulation to a semi-analytic galaxy evolution and a semi-numerical reionization scheme. So what we end up doing is essentially you take the density distribution and the dark matter merger trees from the n-body simulation. We post-process the merger trees with a semi-analytic galaxy evolution model. And this includes essentially gas accretion, star formation, the most massive stars, explosive supernovae, and enrich the galaxy with metals and dust, and also emit sort of the ionizing photons. And we have also a prescription how many ionizing photons actually can escape into the intergalactic medium. And then on the fly, for each snapshot or time redshift, we essentially compute, if we have all these galaxies, how would the ionized regions grow? And because we track this on the fly, we actually can also account for radiated feedback from reionization. Okay, so this is a framework with which I did my 2 simulations with whether the faint or bright galaxies drive it. And so here you see the results. So the key thing about these simulations is they actually reproduce the Planck optical depth. They also reproduce the UV luminosity function at redshift 5 to 10, and also the Lyman alpha luminosity function at redshift 6.6 and upwards. So in the top row, you see the ionization fields for the scenario when the faint galaxies drive reionization. So as before, you see like the smaller ionized regions, and in blue, in red, you see the Lyman alpha emitters. And in the bottom panel, when the bright galaxies drive reionization, and you already can see your ionized regions are larger, they're actually also slightly more spherical and more clustered. All right, so the key question now is like, Lyman alpha emitters have a special sort of property. So because the Lyman alpha radiation is sensitive to neutral hydrogen, what happens is that they essentially need to lie in the most ionized regions. And so we just wanted to check whether in our Lyman alpha emitter model, they really lie in the ionized regions. And so what you see here on the left side, essentially the neutral fraction of the IgM versus the overdensity. And then you see in the colorful contours where the Lyman alpha emitters lie. And what you can conclude from here is essentially they lie in more or less very ionized regions. So this is essentially crucial if we want to understand the cross-correlation function. And so what this allows us to do is to formulate an analytic estimate for the cross-correlation function. And what essentially we find that during reionization and after heating, the small scale amplitude scales as minus the neutral fraction of the IgM and the density in the neutral regions. And so this is actually really interesting because now you can compute for these different scenarios whether the average density in the neutral regions differ. And indeed it does. So if you compare the scenarios where the faint galaxies drive reionization, what you essentially can see that the ionization fields, they follow more closely the underlying gas density field. And that results in, if you look at the average overdensity of the neutral region as a function of the IgM neutral fraction, that we can see the average overdensity is lower. And so this means vice versa, if reionization is driven by bright galaxies, this average overdensity is slightly larger, particularly towards the end of reionization. And here it's also interesting to note, if you essentially were going to measure the 21 centimeter signal in a bunch of regions which don't host Lyman alpha emitters, what you will see, you essentially would detect on average a slightly larger 21 centimeter signal than in a scenario where the reionization would be driven by the faint galaxies. And I think the other thing which you really notice, which is shown here in the dashed lines, essentially they show like a far larger variance across these regions. And this is purely because you have more symmetric regions and they follow less the underlying filamentary structure. Okay, but now back to the cross-correlation amplitude. So if we now look at the cross-correlation, which we have computed from the simulations, these are the results. So you have here on the left-hand side, the scenario where faint galaxies drive reionization, and on the right-hand side, where the bright galaxies drive reionization. And as we expect, as reionization progresses, the overall 21 centimeter signal drops. And so the cross-correlation amplitude on small scales starts dropping because your overall 21 centimeter signal is dropping. So the difference between this no 21 centimeter signal around the Lyman alpha emitter and the global mean becomes smaller. The other thing I think you immediately can notice, if we compare like when the universe is roughly 50% ionized, and that happens in both scenarios around a redshift 7, you can see in the case where the bright galaxies drive reionization, actually the amplitude is larger than if the faint galaxies drive reionization. So this directly reflects this density in neutral regions, which is larger if bright galaxies drive reionization. So far, this was very predictive, but we actually wanted to go a step further and ask ourselves, can we actually describe the entire cross-correlation function analytically? And so if you think about this, essentially what the cross-correlation describes is sort of the average profile, 21 centimeter profile around a Lyman alpha emitter. And if that is the case, then actually you can use the size distribution of the ionized regions around the Lyman alpha emitter to formulate then via the cumulative distribution function of that size distribution, an analytic estimate for the cross-correlation function. And if you fit this now with a dotted line, for instance, with a log normal function, you actually find that a log normal distribution reproduces these kind of shapes rather well. All right, so this was the cross-correlation function. And of course, these characteristics or dependencies on the ionization morphologies, we also find in the cross-power spectra. So how do we find this? First of all, sort of the typical size of the ionized regions you can see in the sign change of the cross power. So what you see here in solid lines is essentially negative. What is dotted here is positive. So you can see around these scales, you see a change in the sign. And so this sign change essentially traces a typical size of the ionized regions. So definitely you can see the typical size of the ionized regions are different in these two scenarios. But I also want to highlight here, if you look at the large scale power, you have a stronger, more large scale power in the case when the bright galaxies drive reionization. So when your average density in the neutral regions is higher. The question remains now, which of these features can we actually measure? And so what I did for a survey, which assumes sort of SKA1 low and some kind of Roman Grism survey with a redshift uncertainty of 0.02, a Lyman alpha depth, we detect everything down to 10 to 42.8 ergs per second, and maybe a rather optimistic field of view of 10 square degrees, then you see here in the shaded region, essentially the observational uncertainties. And I think what you immediately can see that it would be hard to detect scales where we can see or trace a typical size of the ionized regions. And we will mostly rely on the large scale power. So, but in general, I think it's also worth asking what type of 21 centimeter in galaxy surveys would we need to do this, and how does this scale? So I think Andre mentioned this already a little bit. I think I go a little bit into the detail in a different way. So in generally, when you think about the uncertainty of the cross power spectrum, it is given essentially by three contributions. So on the one hand, you have the sample variance from the 21 centimeter as well from the galaxies. And then from the 21 centimeter signal, you get also the thermal noise, which depends on your radio interferometer. And for the galaxies, you actually also have the shot noise. And so how do these determine, and on which scales do they determine your uncertainty of your cross power spectrum? So first of all, if you look at the shot noise from the galaxies, we can see it scales with the number density of the galaxies. So the higher the number densities of the galaxies, the lower is the shot noise. And similar, the lower the redshift uncertainty, also the lower is the shot noise. So the lower the shot noise is, the more you can actually detect, or the lower are your uncertainties towards larger K modes. I looked at this also to put this a little bit more into context. So what you can see here is, for instance, the cross-power spectrum redshift 7, and in gray you see the observation uncertainties for our default parameters here. And so if you, for instance, change here the redshift uncertainty, you can see how your signal-to-noise ratio of the cross-power spectrum redshift 7 changes. And you can clearly see if you decrease or increase your redshift uncertainty, then your signal-to-noise ratio goes down, and you also shift your sensitivity to larger scales. And similar, the same exercise you can do for the number density of galaxies. So this is basically encoded here in terms of the minimum Lyman alpha luminosity that we are going to detect. What this means here, essentially, if we have high Lyman alpha luminosities, we have less Lyman alpha emitters, and if you have low Lyman alpha luminosities, we have more Lyman alpha emitters. So therefore, as we go basically decrease our Lyman alpha luminosity, the more galaxies we will see, and also the higher will become our signal to noise, and the more slightly we can push also to smaller scales. And the next part, so this was mostly like limiting sort of the small scales or large K modes. The thermal noise from the radio interferometer sort of increases with increasing K. And what you can do essentially to lower this, mostly I think it will end up in the intermediate K modes, you can increase the observing time or the number density of your antennas to push this down. And finally, the sample variance essentially dominates the uncertainties in your low K modes or your large scales. And this is what you can do by increasing essentially the survey area, so the field of view. And so if you show you here a similar plot, if you now plot again your signal to noise ratio as a function of the field of view, you see also very nicely as your field of view becomes larger, your signal to noise ratio becomes larger, and you also can push slightly to smaller scales. All right, so I think what was also, also pointed out, you already can see there is sort of a tension in terms of if you, from the 21 centimeter side, you would prefer to have large surveys to push down your observational uncertainties. While from the galaxy survey side, you actually would like to have like deep surveys to reduce your shot noise. But I think combining both will be really hard. So coming back to the question like, okay, how can we distinguish our two models? In the past few days, I was wondering, okay, if I go through my survey parameters, so what I mean by here is the survey parameters is the redshift uncertainties, which you see here in the top, the minimum Lyman alpha luminosity, so the depth, and your field of view. And I was wondering, okay, for which survey parameters could we best distinguish between, in this case, our two scenarios? And so essentially what this is, you sort of compute a chi-squared, and I did it in this case just for summing it over the redshifts, the cross-power spectrum redshift 7, 8, and 9. This is just to have like a first idea, and it's very much in progress. But I think what you already see, if you assume a redshift uncertainty spectroscopy-like, GRISM-like, or narrowband-like, you see directly for narrowbands, we get very rather low sort of chi-squared values, which means that we cannot well distinguish between the two models. So the higher this value is, the better you can distinguish between the models. And you already see like with GRISM, and you can do a much better job. And actually the difference between GRISM and spectroscopy seems to be not that large. I guess it's mostly because the constraining power comes essentially from the large scale modes. And this is also very interesting because what you also see here from the contour lines essentially is that it does not seem to depend very much on your survey depth. And this is, I think, another indication that most of the difference comes from the large scale power, I assume, because we cannot really track the sign change here in the cross power spectrum. And So this sounds maybe rather negative, or I think also, but I could find from here that the most constraining power essentially, or differentiating power, comes from the lowest redshift, because at higher redshift, you don't have many Lyman alpha emitters. But I think one thing I want to also highlight is these simulations were tuned to the observation constraints we had pre-JWST. And so recently we have developed a new model where essentially we have changed the IMF and it becomes top heavier in galaxies that have a higher specific star formation rates. And this has two implications. So on the first, you have far more galaxies with a top heavy IMF early on. So reionization starts earlier, but reaches the middle of reionization similarly and has very similar ends. So there's not much difference. But the key point is, like, early on, you already have ionized regions. And secondly, what also happens if you have a more top-heavy IMF, you have more ionizing photons output. And so you can also produce a higher intrinsic Lyman alpha luminosity. And so this brings me back to the right panel here. So what you see here is the Lyman alpha luminosity function. The dashed dotted shows you essentially the salpeter IMF, the solid line, the evolving IMF, which is top heavier at higher redshifts. And what you can take away from this, essentially, that above redshift 8, your number density in Lyman alpha emitters increases around the typical Lyman alpha luminosities you would target in observations, around by 0.6 dex.
And we are almost at the end of the time.
Yes. So what you see then also, if you go to higher redshift, this difference becomes more and more stronger. So I think this is just sort of the positive note, I think, where we need to check. And therefore, then I leave you with my summary. Thank you.
Thanks for the very nice talk. And then we have some questions from here. Prashun, please go ahead.
A nice talk. So I was just wondering, so you are going to K modes 1 megaparsec or even beyond. So is the redshift space distortion already included in your delta?
No, they're not included.
But it will have some effect probably in the cross correlation as well?
Possibly, yeah, I guess some, but I'm not entirely sure. I'm not sure. I would need to think about it a bit more.
Thanks.
Hi, Anne. Thanks for the very nice talk. The comparison that you did for the slit spectroscopy and the GRISM, you mentioned that they were comparable, but I noticed that your field of view axis is the same for both. And I think that's not really fair, because spectroscopy, we're not going to have 10-degree field of view spectroscopy because we need to follow it up. And it's a very expensive kind of thing. So like more than like 1 or 2 is going to be super, super hard. And if I interpret that correctly, it seems like it even strengthens your claim that we can really only do it with GRISM. Do you think that's fair?
Yeah, so I mean, this is essentially sort of the takeaway, I think, also from this. No, I totally agree with you. Spectroscopy, we can't on these large field of views. This was mostly to scan the parameter space and get an idea.
And in this case, did you have like an SKA type layout? Maybe I missed this with like, what was your foreground?
Yeah, so essentially we use the SKA stations, from SKA1 low. We only include baselines up to 10 kilometers. And otherwise, it's essentially all the uncertainties are computed by 21 centimeter sense, I think, similar to what Summer has been doing.
Any other question? Okay, if not, let's thank the speaker. that, we come to the end of this particular block. Let's thank both the speaker of the session, and we break for